In this video, I'm going to go over the basics of electricity, just an introduction. The PowerPoint's a little bit longer, but I'm just going to do the first part of this PowerPoint in this video. All right, so we're going to talk about the movement of electrons. It's an invisible force that provides light, heat, sound, and motion. Right, so first we need to understand what makes electricity work. It's these atoms. We've got to look at the metals. All right, so we've got to look at the atoms and the subatomic particles before we can actually understand electricity. So electricity at the atomic level, right, components of the atom. This is the nucleus here in the middle, the center portion of the atoms containing the protons and the neutrons. You got your protons that are positively charged atomic particles. We've got in this one 1, 2, 3, 4. Tells us which element it would be. If we go back here, number 4 is beryllium. Okay, and then the neutrons are also in the nucleus, and it's an uncharged particles. All right, so 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. All right, and those are typically not the same number as a proton, but they don't have a charge. So it actually took them a while to find neutrons because there's no charge. They just noticed that the mass of the atoms were more and couldn't understand where that extra mass had came from. And that's what led them to the discovery of neutrons. All right, so the atomic number is equal to the number of protons in the nucleus of the atom, like I was just talking about. By looking at the atomic number, we were able to go back to the periodic table and figure out which element this was. All right, the atomic number identifies the element. Okay, well, if it's a neutral atom, the number of protons and the number of electrons are going to be equal. And because protons are positively charged, to be neutral, it would have to have the same number of negative charges. Well, electrons are negatively charged particles, and they're out in the electron cloud in their orbitals. Right, so it's orbits in which electrons move around the nucleus at an atom, and depending on where it is, it could be like going around it, or it could be going in kind of a dumbbell shape, or depending on which level it is in. All right, so this is kind of a crude representation of that, just showing those s orbitals. And yes, these 4 would just be going around in this case. All right, but we really only care about that outer shell. Those valence electrons are the ones that are actually combining. They're the ones that are causing, either they want to get rid of electrons or they want to gain electrons. They all want 8 in their outer shell. And I guess I shouldn't say all, because helium is fine and stable with just 2. So they just want to fill up their outer shell. So if it's this first shell here, then it just wants 2 to fill up its outer shell. Or in this case, it would want to lose 2 so that it would have a full outer shell. So in this case, the octet is one of those exceptions to the rules, because we always have that. But we're only looking at those electrons in that outer shell. The ones underneath it really don't mean as much to us. All right, so this is a horrible, 2D representation of where all the electrons are. But again, let's just look at this outer shell. This one would be in that s orbital going around. But atoms like to have their valence ring filled, whether it be 2 for helium, or around that, or 8 for the rest of the chart, right? So it will either gain or lose electrons to do this. Right, so this is, like I said, kind of an old style representation of where those electrons would be found. Copper, it shows 1. If you're in chemistry, you know that you have like copper 1, 2, and 3. I think there's 3 different ones, but this one's showing that copper 1. Whenever we get into the transition elements, whenever we get to another periodic table in here, I'll show you where they fill in. Whenever it starts filling into those d orbitals, it gets a little different because those energies are so close that they kind of jump around a little bit, depending on the element. Not all elements do that, though. So how many electrons are in the valence orbital? Right, it shows 1. Right, so is copper a conductor or an insulator? And I guess it really should show you before that a conductor is going to move its electrons. This copper wants to lose an electron, so it wants to release it so it can have a full outer shell. All right, so that would make it a good conductor. An insulator would be one that wants to gain electrons, or really, ideally, it doesn't want any electrons at all, and that would make it the best insulator. But whenever we're talking about elements, a lot of times it's those that want to gain electrons, though. All right, so why are metals good conductors? In metals, the outer electrons of the atoms belong to a cloud of delocalized electrons. All right, so right here, these electrons in that outer shell, say this is copper, it's got one electron, and they are just going to share these electrons in a random order. Right? They're no longer firmly held by a specific atom, but instead they can move freely through the lattice of positive metal ions. Normally they move randomly here. Okay, so this is just a standard, like say these are copper, any kind of a metal. Those electrons, they're actually sharing them because none of them really want that extra electron, so it's constantly passing it off. It's passing it around. It actually is like a cloud, it's said here, of delocalized electrons. And that's why metals conduct that electricity so well, because it's already moving those electrons around. Now we just need to add a little charge to it, and they'll go in order. They'll line up and actually move those in a straight path, going to that positive. The cathode is positive, and it's going to be attracted that way to it. Okay, so whenever we look at this side, all of the blue are metals. So all of those are considered good conductors. These right here are your semiconductors, and these are our insulators. Okay, they want the electrons, or these right here don't want anything. Right, and then these are actually wanting the electrons. So they're not going to send those electrons on. They're not going to conduct that electricity. All right, so it's a metal. Why don't we use it? All right, well, silver is the best known conductor, but in an oxygen-rich environment, it tarnishes and is very expensive. All right, gold is not as especially good at all. It's a little too soft. It's very expensive. It is considered better than aluminum, but aluminum's a lot cheaper, and so a lot of times they'll use aluminum. All right, the metals in the first column are way too reactive. All right, you try to use this, and you're going to have a fire. All right, the same thing with the second column. So in elevated temperatures, calcium and magnesium are going to burn, and they're going to produce nitrogen and oxygen. All right, so we talked about metals. Now we need to talk about conductors and insulators. All right, so conductors, what we just talked about, these are the metal. And we understand, hopefully by this point, why it conducts that electricity. Right, those electrons are moving already in this cloud. Now we add some extra electrons with a little bit of a charge, and it's going to move through the wire. Right, the insulators. Right, notice most of this is like rubber or plastic or something like that. Mostly the insulators are going to be compounds that are stable compounds that aren't going to react. And that's usually what you see. Whenever we look at just like non-metals or semiconductors or something like that, those are usually the compounds that they're made out of. Carbon's very common. Right, so just some examples of those insulators. And like I said, we're looking at non-metals, we're looking at the semiconductors, those metalloids there in the middle. Their outer shell is not full. Okay, it needs 2 more valence electrons, and so it's going to attract those electrons. And it's not, instead of sending it on because it doesn't want it, it's going to attract it and it's going to keep it. All right, so that's why it would be considered an insulator. All right, so let's look at these. We've got all of these are solids. The reason why a lot of times you don't see any of these non-metals is because they are gases at room temperature. So mostly they're going to be solids that are compounds. All right, they've already reacted. They don't need those electrons. All right, but right in here is usually carbon. You'll see silicon, sulfur, some of those. And here's just a neat periodic chart that I found that talks about the electrical conductivity. All right, showing which ones actually conduct electricity pretty well. Okay, and again, these conduct electricity pretty well, but they're not real stable, so you wouldn't want to use those to conduct those electricity. A lot of times you'll see alloys kind of gets the best of both in that way. Whenever they mix metals, whenever you mix metals, it's called an alloy, and you can get maybe the conductivity of silver without the cost of silver or something like that. All right, so electrons can be influenced to move in a coordinated fashion through the conductive material. So we talked originally about that cloud is kind of random. Well, we can make it be in a conductive material. We can coordinate those to go in one direction. This uniform motion of electrons is what we call electricity, or electric current, to be more precise. It could be called dynamic electricity in contrast to static electricity, which is an unmoving accumulation of electric charge. I'm sure you've done that, especially this winter. Just like water flowing through the emptiness of a pipe, electrons are able to move within the empty space within and between the atoms of a conductor. The conductor may appear to be solid to our eyes, but any material composed of atoms is mostly empty space. So the liquid flow analogy is so fitting that the motion of electrons through the conductor is often referred to as a flow. Right, so let's examine some of that a little bit closer. All right, so a system of conductors and components forming a complete path for current to travel. These are some of the properties we're going to look at. All right, voltage, current, and resistance. And those are the things you need to understand to work these problems. All right, so let's start with voltage. All right, Alessandro Volta, right, was an Italian physicist known for the invention of the battery in the 1800s. The battery made by Volta is credited for the first electrochemical cell. It consists of two electrodes, one made of zinc and the other made of copper. Right, so zinc and copper. The electrolyte is either sulfuric acid mixed with water, a form of saltwater brine. So what's happening here is you've got a reaction going on. All right, whenever this reaction happens, it's going to release electrons. All right, so the new compound does not need those extra electrons to be stable. So it's going to release those electrons. Well, this reaction that's going on over here needs electrons to be stable. Right? So just like whenever a reaction happens and the new compound that's happening here it doesn't need these electrons, so it's going to shoot them on out. There is going to be an exothermic reaction. It's going to have energy that's going to be released because the new compound doesn't need as much energy within its bonds to be stable. So it's going to release that energy. It's also going to release these electrons. Right, so it pushes those electrons in here because negatives are going to repel negative. Positive and negatives attract, negative repels negative. So it's going to be released into this wire. Well, just like we talked about, they're now in this cloud. It's going to be sharing these electrons. It's going to be moving them. Well, with that extra force, then it's going to negatives repel negatives. It's going to push it on out. And it's going to be attracted to this reaction going on over here that needs those electrons. So now these positives, right, the reaction's happening. We have positive charges over here. These electrons are going to be forced over here. They're going to be attracted. All right, so there is a force there by the attraction on this side, repelling on this side. All right, so it's pushing on through. And those are called volts. Also, it's kind of like you put electrons in it, right? There's also a force there because of the exothermic reaction. I hope I'm explaining this to where you can understand it. So let's move on to the next one. But those are volts with a capital V. And sometimes you'll see this represented as an E. So don't be confused whenever you're researching if you need some more help if you see an E there. All right, so voltage is a force that pushes the current through the circuit. In this picture, so we're going to relate this to a stream, so maybe you can kind of work with that. In this picture, it's like gravity. All right, so in this picture, it's pulling it down, well, attracting, earth attracting, that water we won't get into all of that. But in this case, we're going to look at it as gravity. So it's pulling the water. There's a force there. Okay, kind of like here, the electrons are being pushed away from the other negatives. Okay, so that is voltage. It's that push or that attraction. All right. Also, let's talk about resistance. All right, so resistance is a friction that impedes flow of current through the circuit. All right, rocks in the river. So if we're talking about the river again, we've got rocks, beaver makes a dam, something like that. You've got things that are going to get in the way of the water moving down the stream. All right, so the gravity is still pulling it, or current is being pushed, or in this case, pulling. Again, we won't get into this, the details of that, but you understand that it's still got that force. All right, so now the current, the water current, there is resistance of the rocks or the dam from the beaver, and those are considered ohms. That's what that's measured in. All right, so now let's talk about that current being like the water, it's flowing. All right, the actual rate of the substance that is flowing. So what rate is it going by? In this one, notice it's going a lot slower than the one before it. All right, so a current is measured in amps, or A. All right, an ampere is 1 coulomb per second, is what it's defined as. So 1 ampere would be 1 coulomb per second. Right, well, what is a coulomb? Well, it's the SI derived unit of electrical charge, and it's approximately equal to 6.24151 times 10 to the 18th electrons. Right, it's got its name from Charles Augustin de Coulomb. All right, so here's another way of thinking about it. We got a couple of varieties here. We've got a tank. All right, again, there's pressure because of this big tank here. There's pressure going into this pipe. All right, so the tank is like our battery. All right, it's pushing pressure into the pipe. This is like our wire. All right, so the flow of electric charge is measured in amperes. All right, so when the faucet switch is off, is there any flow current? Well, no, it's not moving. All right, so we have 0 coulombs per second, or in this case, water droplets, moles, however you want to measure it. All right, so when the faucet switch is on, is there any flow or current? Well, yes, right, it's flowing. So just like whenever we were looking at the battery, if I was to break that wire or put a switch on it and open that wire up, it's not going to move. Right? Those electrons are going to stay because on the other side, that positive is no longer attracting it, so it's just going to stop. Yes, there's still pressure there. Yes, those electrons can still move, but once you break that wire, you open that switch, it's not going to move because those positive electrons are no longer attracting it. In this, I open up the faucet and it allows it to flow, right? Which is amperes, all right? That rate that it's flowing. So in this case, it's turned off, all right? I've got it open. These electrons are no longer being attracted by, I've opened it, I've put a break in it. So these electrons are moving, but there's nowhere to go now. It stops. Right? These positives are not attracting it anymore because it's got a break in the wire. But yes, there's still pressure there pushing those electrons away because negative repels negative. So there's still that pressure though, just like in that tank before. Right, so there's no current when the switch is off. When the switch is on, there's a current. All right, so we've been talking about it like this electron flow in the scientific method, or the scientific way, but we're going to use the conventional method in engineering. And it's really still the same, I guess, concept that there's a flow. It's just drawn as like the positives are moving, and we know that that's not possible. But I don't know if you've noticed with this class so far that engineers do something a certain way, and they've always done it that way, and everybody understands it that way, so they just continue to do it that way. So this is called a conventional current, assumes that the current flow out of the positive side of the battery through the circuit and back to the negative side of the battery. This was the convention established when electricity was first discovered, but as we can tell now, it is incorrect. The electron flow is what actually happens, and the electrons flow out of the negative side of the battery through the circuit and back to the positive side, just like I've been explaining here. But we're going to, when we draw the battery and we draw the lines, we're going to go ahead and use this conventional current simply because we're in an engineering class and engineers have always done it this way and they're really not going to change. So yes, this is not really the correct way of displaying it, but we're going to go ahead and use this way. All right, so the direction that the current flows does not affect what the current is doing. Thus, it doesn't make any difference which convention is used as long as you are consistent. Both conventional current and electron flow are used. In general, the science disciplines use electron flow, whereas the engineering discipline uses the conventional current. All right, since this is an engineering course, we are going to use the conventional current. As long as you understand that this isn't really what's happening, it is this. We're just going to draw it in the way that engineers have always expressed it. All right, so let's look at voltage again. All right, so the force or pressure that causes current to flow is measured in volts. All right, so right now, yes, there's still that pressure. All right, it's like these water molecules are still forcing itself up against here. All right, but there's nowhere to go. So when the faucet switch is off, is there any pressure or voltage? All right, yes. It's still pushing against the pipe or the tank and the faucet. When the faucet switches on, is there any pressures or voltage? Well, yes, still pressure. It's still pushing up against the tank, it's still pushing up against the pipe, but now it is allowed to open. All right, and so the volts are going to stay the same. Okay, we're still going to have, with those electrons, are still going to be releasing the same number of electrons, whether it's on or off. And those negatives are still going to be repelling, whether it's on or off. So here's voltage. It's off. Okay, the battery provides voltage that will push current through the bulb when the switch is on. Okay, now resistance. Okay. What happens to the flow or current if a rock gets lodged in the pipe? Okay. Well, the flow or current decreases. Now we're assuming that this rock is not enough to fill up the pipe. Okay, so there's still some going through. All right, so it's going to slow down that current. That's what resistors are for. If your voltage is too high, then it's going to blow your light or whatever it's using. So we need resistors in there. We need something to slow that current down. Okay, so it's on. Notice that the light bulb itself is resisting some of that current, right? And it's actually that energy is being released as light. So this wire is a little bit larger than that little filament inside of a light bulb. So these electrons are being forced into a little bitty wire, which is going to cause resistance. Basically, electrons are moving and they're going to bump into more stuff. All right, so then it goes into a littler wire. It's going to bump into even more. It's going to release some of that energy, and when that energy is released, it's going to release it as light. If it's in the middle of a resistor, it's going to, again, bump into stuff inside that little resistor. And we'll have a lab on resistors. But the resistor is just going to kind of bump into it, and it's going to kind of get in the way, and it's going to slow that current down. Right? And it's going to, because of that resistance, that making it into a smaller wire, which causes it to kind of heat up and release some of that energy. Okay, so here we have a resistor. A light is also considered a type of resistance. So, okay, here I'm going to stop. We're going to talk about measuring the voltage for the lab probably in tomorrow's activity. So for now, I just want to make sure that you understand electricity. where it's coming from, what volt, resistance, and current are. If you didn't quite get it from my PowerPoint, I found some really good information on how stuff works. I've typed in how does a battery work. I also found some real basic stuff on Khan Academy, K-A-H-N, Khan Academy, on how a battery works. And they did a really good job at kind of, I guess you could say, dumbing it down to where I could truly understand it. So it was really good. So look at Khan Academy or how stuff works and say, how does a battery work? How does current work? How does, really, I got the best information from putting how a battery works. So look at some of those, make sure you understand it, so that way tomorrow when you do the activity, it'll make a little more sense, and I'll also show you how to use a voltmeter with that as well. So hopefully this PowerPoint helps.